Now that we have developed a number of differentiation rules, in fact all the rules that we need for our purposes, and we have seen how those can be applied to basic functions in order to obtain an easy formula for their derivatives, we can extend all of this machinery to more and more functions in a very simple way. For instance, today we're going to be looking at the derivatives of hyperbolic functions, and the theoretical part, the video, is going to be fairly short. Most of the class will be devoted to your practicing on these things. So for instance, to get the derivatives of the two basic hyperbolic functions, all we need to do is use the exponential rule and some other basic rules. And we need to remember that, of course, hyperbolic functions are defined through formulae. So for instance, the hyperbolic sine is given by e to the x minus e to the minus x over 2. So if we need to take its derivative, remember that the 2 is a coefficient as stays, we apply the addition rule on top, and now all we have to do is compute the derivative of e to the x, which is a piece of cake, and the derivative of e to the minus x, which is also an exponential combined with the chain rule, and gives us, of course, minus e to the minus x. Once we combine that with the existing negative, we end up with e to the x plus e to the minus x over 2, which we can recognize easily as being the hyperbolic cosine of x. We do exactly the same thing with the hyperbolic cosine. The formula is practically the same, except that we have a positive instead of a negative. So we end up with e to the x minus e to the minus x over 2, which we recognize as the hyperbolic sine. So again, two fairly simple formulae. The derivative of sinh is cosh, and the derivative of cosh is sinh. I previewed this fact when I introduced hyperbolic functions, and again, remember that these two derivatives are very close to the ones that we have for trigonometric functions, even though we haven't seen the derivatives of those functions yet. Now, how do we get the derivatives of the other hyperbolic functions? Well, they're pretty much in the same way, using those two basic derivatives, the derivative of sinh and the derivative of cosh, together with the quotient rule usually. Now, how about the derivatives of inverse hyperbolic functions? Well, we can obtain those in two different ways. We can either use the fact that, once again, these hyperbolic functions have formulae, and therefore we can use their formula and apply basic differentiation rules to that, or because they are inverse functions, we can use implicit differentiation. For instance, let me show you just how this can be done on the inverse hyperbolic sine, and then you can follow the same procedure for the other functions. So what we can do is we can use its formula. Remember, the formula for the inverse hyperbolic sine is ln of x plus square root of x squared plus 1. Now, first of all, I'm going to rewrite that square root in order to make it ready for differentiation. And now we're going to use differentiation. First of all, chain rule, derivative of logarithm gives us 1 over the inside. And now, because I'm not going to do anything more with it, I write it back as a square root, times the derivative of the inside, which is going to be equal to 1 plus 1 half x squared plus 1 to the negative 1 half times the derivative of the inside through the chain rule, which is 2x. Those twos cancel, we can beautify it a bit, and it looks like this. And that's still not very good, still not very simple enough. So what we're going to do is we're going to do a common denominator on the second bracket, and now it's much better, because now you'll notice that the denominator of the first fraction is exactly equal to the numerator of the second, which means we can cancel those two, and we end up with this nice looking formula. So the derivative of the inverse hyperbolic sine is simply 1 over square root of x squared plus 1. Fairly simple thing. Alright, now we can do the same thing, we can achieve the same result by using implicit differentiation. What we have to remember is that if y is the inverse hyperbolic sine of x, that means that the hyperbolic sine of y, or sinh y, is equal to x. Alright, let's take derivative left and right. So that means on the left we end up with cosh y times y prime. On the right hand side we end up with 1. We solve for y prime, that gives us 1 over cosh y, and then we use the basic identity for sinh and cosh for hyperbolic functions, which tells us that cosh is the square root of sinh squared plus 1. Of course, here we have sin squared of y. We want to go back to x, but that's easy because sinh of y at the beginning was equal to x, and so we end up with exactly the same formula, 1 over square root of x squared plus 1. If I went a little bit too fast for you, it's okay, just rewind, watch it again, and pause whenever you need, but make sure you understand how this is done, because then in class and later on, I will ask you to do something very similar on the other inverse hyperbolic functions.